Okay. Good morning. 8:32. Let's do it. Okay. So today's agenda. I'm going to continue with the introduction example to 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 introduce what are we going to learn over the next 13 weeks. Okay, and hopefully this will inspire you. Then we're going to start our first topic with centric symmetry and unsymmetry bending. Okay, so I will start teaching where you left off or where Dr. Koshi left off into P04. Okay, then on Friday we have lecture from 8:30 to 9:20, and then lecture again from 10:30 to 11:20. So it's 2 hours of lecture. Okay, right. So let's continue with our example. Okay, so when we left on Monday, right? I briefly just do a quick recap. We look at a table like this, right? That has material properties and what these material properties means. Okay. So all these material properties were acquired from uniaxial tensile test. It can be uniaxial tensile, uniaxial compression, uniaxial shear. Okay. So that's why you have them as tension, compression, and shear, each on different columns. Okay. So a student asked me, if the number is not there, can we use like for example, over here you don't have any number over here. Can you use the 400? The answer is no. Okay. Because any material in tension and compression or in shear will have different properties. Okay. Then I drew for you guys. Okay, I drew for you guys. We pick an element out. Okay, I drew for you guys what this element will look like. And because the stresses is just in one direction, you have stress X. And then we are able to construct Mohs circle. Okay, so in Mohs circle, this will be your point X. This will be your point Y. Okay, and point Y is 0. Over here as Y is 0 because there are no forces applied to it. Okay, so then you draw your circle. Then we call stress 1 and stress 2. So this over here is your stress 1. This over here is your stress 2. Are your principal stress. And then when we finish off, okay, we realize that the tension and compression values given are the principal stresses. Okay, are the principal stresses because based on uniaxial test. Okay, one direction. Then we come to an actual loaded structure. Okay, we come to an actual loaded structure. And we realize that the loaded structure is not the same as how the material properties were acquired. It's not the same at all, right? Over here, all are unidirectional. Over here, this is unidirectional, unidirectional, unidirectional. Over here, in an actual application, it's no more unidirectional. So why do I mean that it's no more unidirectional? You have compression, okay? You have a torque, so you have Px, okay? Which is, if you look at the structure, it's under axial loading. Okay. And then the 2300 will be a moment in X, or for this case, the torque in X. Okay, so this is your torque in X direction. Okay, and then we have a moment in the Z direction. Okay, so moment in the Z axis. Oh, Z, come on, Eugene, wake up, wake up. Too early. Z axis. Okay, so the loading condition now is not the same as what you see over here, right? Then how do we choose the material based on the data given here? How do we know that the structure will not fail. Okay, that's where we really have to be really cautious about this, right? So when I was a young engineer, I said, okay, just care about one direction, the rest ignore. No, you can't do that. Okay, so now I'm going to teach you the procedure on how to determine the stress state in this structure over here. Okay, and so that you are able to use the data from here. Now, some of when I was younger, I would say if that's the case, right? If that's the case, if I'm not sure, okay, when uncertain, about loading condition, okay, we can always use higher factor of safety. Okay, so I write down here factor of safety. So what do I mean by that? So we have looked at a formula on Monday. We realized that factor of safety is equal to stress yield divided by stress allowable. So we realize that this is for ductile material. Just to recap. Or it can be equal to stress ultimate strength divided by stress allowable. Okay, and this is for brittle material. Right. So if you are uncertain of the loading condition, okay, when uncertain, when not sure, okay, use higher factor of safety. Right? When you're not sure, you use higher factor of safety. And this is not right. If that's the case, what's the point of having a degree? Okay, my mom could design a structure when we use a factor of safety of 10. Okay, yes, she could. It's safe. She will use 10. She'll use 20, right? But that's not the case. Okay, especially for mechanical engineers. Why? For mechanical engineering, okay, we generally design structures that is on the move. We don't always design structure that don't move just like that don't move. Only civil engineers design structure that don't move. We design structures that move. That is where we cannot use factor of safety that's too high. Civil engineers, oh, we can use factor of safety of 3, 4. Yeah, your building ain't going anywhere, or except you might get some earthquake, right? So for us, okay, as mechanical engineers, we design things that move, flies, go under the water whatsoever. Okay, so we cannot use very high factor of safety. Okay, now let's look at this structure. How do we select the material? Okay, so this is where I'm going to introduce you to two sets of formula that are critical in structure design, whether in static or in motion. Okay, and how these formulas can be incorporated to choose your actual materials. Okay, so the first thing we're going to do is we are going to go into failure analysis. Okay, we are going to go into failure analysis. Now let me start on a new page. Okay, we are going to look into failure analysis. Okay, so I'm just going to copy the same shaft. Right. Okay. So this is the structure that we have. We are going to look at failure analysis. So to do failure analysis, right, we are going to look where the structure or which part of the structure is going to fail. Okay. So how do I mean by that? So I'm going to look at 4 points. Okay, on this chart. Okay. So I will use a different color. Hopefully you can see. So I'm going to draw 4 elements. 1, 2, 2, 1 down here and 1 over here. All right. Then I'm going to give them names. Okay. I'm going to call them element A. The one at the top is element A. Then we have element B. We have element C. And then we have element D. Okay. So we have element A, B, C, and D. Okay. So by looking at all these elements, right, we need to know which element will fail. Okay, so we are making the assumption that this phase, okay, on this phase over here is where fracture will occur. Okay, we make that assumption, but exactly at which point? Is it element A, element B, element C, or element D? Okay, so we start analyzing a structure like this. Okay, we start analyzing. So I'm going to draw a cross section 2D view now. Okay, I'm going to construct a 2D view. I'm going to draw a circle. This is a 2D view. All right, so we have our transformation. Yeah, I'm going to draw a transformation. So based on the transformation that we have, so this is your Y. And then over here, this is your Z. Okay, so now we will have our elements. So I'm going to put in our elements. So your element over here. So this is your element A, element B, element C, and element D. Okay, so this will be our element A, element B, okay, element C, and element D. Okay, so now let's consider axial loading. Okay, so let's consider. Okay, let's do analysis or consider normal stress in the x direction. So when I write down the formula, okay, you'll say, I have seen this before. Okay, so let's consider the normal stress in the x direction. Okay, so let's look at over here. You have moment in z. Okay, you have an axial loading, right, that is going to cause normal stress. So the formula that we are going to apply, okay, is equal to stress x is equal to px divided by a, right, plus or minus, right, my over iyy multiplied by z, okay, plus or minus mz over izz divided by y. Okay, before I go any further, right, what we are doing down here is to find out which element will fail. Is it element A, element B, element C, or element D? Okay, we don't know yet. Okay, this is where the analysis starts kicking in. Okay, So when you look at a formula like this, you all have seen it before in 2P04. Yes or no? Right? So this loading condition is what we call eccentric loading. Okay, eccentric symmetrical loading. Okay, so for this case, when we implement all the formulas, right, this is unsymmetrical loading, which I will elaborate in the first week and second week. Okay, so we are going to learn this in week 1 and week 2. Okay, we are going to learn this for the next 2 weeks in detail. Okay, so now coming back to our structure over here, right? We have a compression of 2,500. Okay, so we know that the first one is going to be minus. Okay, it's going to be negative. The rest we don't know yet. Okay, the rest not don't know, but if